In this last video, we're going to take a look at end behavior of exponentials, logarithms, and we'll even look at the end behavior for a trig function. So here we'll start off with a quick theorem just establishing the end behavior of exponentials and logarithms. Here we have the end behavior of our exponential growth function. You may have seen it referred to that. So here, if I was to graph e to the x, or if you remember what the graph of e to the x looks like, the end behavior should follow fairly easily. So e to the x will pass through 0, 1, and as I approach negative infinity, I have a horizontal asymptote at y equals 0, so it approaches the x-axis, and as I approach positive infinity here, it will approach positive infinity rather quickly. It grows exponentially, hence the name here. So here, just to verify, the limit as x approaches positive infinity here, in this case, well, if x is approaching positive infinity, then we see the arrows pointing upward. Y is also approaching positive infinity. For the left-hand side over here, limit as x approaches negative infinity. So here I have the left-hand end behavior. Here we can see our function is approaching the x-axis, that horizontal asymptote of y equals 0. So that's where we get our two end behaviors from. The next function here, very similar. The next function we have here, this is just your exponential decay function. So all this is, if you're good with transformations, you can look at actually how is this different. Well, in this case, it's really just the negative sign right here on both of these. And if we put that negative sign in front of the x-axis, it just reflects about the y-axis here. So we're just going to reflect about the y-axis, so I should see a mirror image of the graph that I just drew up above. So this time, as I approach positive infinity, that's where my horizontal asymptote is going to be at y equals 0. And as I go to the left, as I approach negative infinity, then in this case, the y value will approach positive infinity. So just to highlight these, here I have limit as x approaches positive infinity. We're talking about the right-hand end behavior. Here we can see our graph is approaching 0. It's approaching that horizontal asymptote. And if I want to talk about the left-hand end behavior, here as x approaches negative infinity, here we see our graph is going upward. It's approaching positive infinity for the y values. Now, logarithms here, we're just going to talk about natural logarithm because that's the most important one. Here, you'll notice right away, if you're looking at this, the limit of the left-hand end behavior actually looks a little bit different. This isn't a typo here. It says limit as x approaches 0 from the right-hand side. The reason for this is that the domain of natural log of x is actually positive 0 to positive infinity, not including 0, right? So we're going to make sure that we use parentheses. Let's just make sure we are clear on that. We're using parentheses around 0 to show that 0 is not included. The domain of natural log or any logarithm is only positive numbers, all positive x values here, so 0 to positive infinity. So it doesn't make sense for me to talk about the end behavior at negative infinity because our function doesn't exist over there. It's undefined. So if I were to graph this function, what I would see this time is I would have a vertical asymptote this time at x equals 0. So this time I have a vertical asymptote at x equals 0. And then it will diverge very, very slowly. And let me actually clean this up a little bit here. It diverges to positive infinity rather slowly. It might look like it's going to level off over here on this end, but it's actually not going to. So here, if x approaches positive infinity, when we talk about the right-hand end behavior here, our function is approaching positive infinity very slowly. This will be a really important idea in, say, Calculus 2. We might need to, and we might care about how quickly things converge or diverge. So here it will diverge to positive infinity. And again, for the left-hand end behavior, again, just notice here we're talking about 0 from the right-hand side because that's sort of the left side of my function. That's as far to the left on this function I can go. So if I go 0 from the right-hand side here, 0 from the right-hand side, I see that vertical asymptote at x equals 0. My arrow is pointing downward. It must approach negative infinity then. So let's take a look at a couple of examples here. So my first example, I want to just determine the end behavior of each of these functions. So here I have f of x equals negative 3e to the negative 2x power. One thing I would just make sure you're paying attention to is what type of function we have here. Here I look at this is an exponential function, which means when I look at the end behavior, I'm going to want to look at the limit as x approaches positive infinity and negative infinity. That's going to change down here when I talk about the end behavior of natural logarithms. So just keep that in mind for our next problem. So here, though this is an exponential, I might want to look at the limit as x approaches, let's say positive infinity first, of negative 3e to the negative 2x. And I look at this negative 3, and I'm very concerned about that. Not so much because of the 3, more so because of the negative sign. I just want to be very careful with that negative 3. So what I'm going to do is I'm going to actually factor that out so that I don't accidentally make a mistake here. I'm going to factor out that negative 3 times the limit as x approaches positive infinity of e to the negative 2x power, so that I don't have to worry about that when it comes to the limit. I can just come back at the very end of my problem and then I'll handle that negative 3. Here it's up to you how you want to approach this now. You could look at this negative 2, you say, okay, this looks an awful lot like e to the negative x. I just have this multiple of a 2. So think about what that's going to do. If you have a multiple of 2 inside of your function, what that actually does, that is a horizontal shrink. It takes everything and sort of pushes it towards the y-axis here. And you might say, okay, basically what happens is wherever it's going to go there a lot faster. So in this case, if I look at the limit as x approaches positive infinity of e to the negative x, well, here as x approaches infinity of e to the negative x, it's still going to approach 0. It's just going to approach 0 much, much faster now. So you could say, okay, I know that this is going to approach 0 because of what I know about transformations. The other thing you could do, if you're not so great with transformations, is you could say, well, let's use properties of exponents here. This says negative 3 times the limit as x approaches infinity. I'm going to think about this as e to the negative x power all squared right here. So here I can now just look at the limit of this inside part right here, and then I'll evaluate the rest of this. So now I can look at the limit of that inside part. Here in this case, let's just go down here. Negative 3, I just said that, hey, if you look at the limit of e to the negative x, we said that was 0 up here. So I have negative 3 times 0 squared, which would be negative 3 times 0, means that this limit should approach 0. So that is my right-hand end behavior. I also need to talk about the left-hand end behavior. So because this is an exponential function, I'm going to look at the limit as x approaches negative infinity here. And a lot of the same tricks we just used for the right-hand end behavior we can do here. So maybe I say, okay, before I even get started, maybe I say I'm going to factor that negative 3 out. Let's do that. E to the negative 2x. And again, you can lean on the information that we stated in the last problem. You can say, okay, I know that this looks like e to the negative x, but I have this multiple of a 2 inside of my function. So what does that do? That takes it and applies a horizontal shrink here. So wherever it's going, it goes there faster. So where does this guy go this time? So this time if I look at x approaches negative infinity, this time e to the negative x will approach positive infinity here. So I could use that fact, or if you're not comfortable using your transformations here, we can apply the same exponent rules that we did in the last part here. So this says -3 times limit as x approaches negative infinity here of, let's say, e to the negative x, all of that squared. So this says -3 times here, e to the negative x, this part right here, let me highlight it, this part right here, we just said earlier that that approaches positive infinity here. So I'm going to kind of quote-unquote plug in positive infinity here and just kind of think about what happens if I take a very large number here. What happens, if I take this very large number of positive infinity and square it? Well, I have a very large number times a very large number. They're both positive. Means I get back another very large number, so that will be positive infinity still. But I have that multiple of a -3 that I do need to worry about. The 3 is not too important. It's the negative sign that's important. And what that does is it's going to change the sign. So rather than approach positive infinity, we are now going to approach negative infinity here. So that does play a really critical role here for the left-hand end behavior of this function. So let's look at this next one here. I have a natural logarithm. So here I have the end, or I want to find the end behavior. So the right-hand end behavior, limit as x approaches infinity of 3 plus natural log of x. If you'd like to, you can go ahead and apply your limit properties, kind of distribute this limit here. I'm just going to sort of do that mentally here. I know that 3 is a constant, so that just stays at 3 no matter what. It doesn't depend on x. And here, if you need to, scroll back up and look at, okay, what is natural log of x approach here? Natural log of x, if we're looking at the right-hand end behavior, then natural log of x approaches positive infinity. So I have 3 plus natural log of x. We know that that approaches positive infinity. 3 plus positive infinity, 3 plus a very large number just gets me another very large number, so it still approaches positive infinity here. If I want to talk about the left-hand end behavior, just be very careful here. Remember, we have a logarithmic function here. We have a natural log here, so that means it doesn't make sense for me to say limit as x approaches negative infinity because those values, those negative values, are not in the domain of this particular function. I have to say limit as x approaches 0 from the right-hand side because that is the left end of my function. That's kind of as far to the left as I can go on this function. So 3 plus natural log of x. And again here I'm just looking at my properties of logarithms. I'm looking at the theorem that I stated earlier. 3 is a constant, so it doesn't depend on x. That will just approach 3 regardless. Here, natural log of x, if I look back towards the top, I know that that is going to approach negative infinity. I have 3 plus negative infinity. That addition of a 3 is not really going to do anything here, so it must approach negative infinity then. So there is my right and left end behavior. Last example for the section I just wanted to talk about briefly. Here I have h of x equals cosine of x. So here, cosine of x, we didn't really give that in the theorem, and I think it's kind of a really interesting question to think about here. So what I would do, if you're not sure, I always like to look at the picture. I think that's going to be the easiest way to understand what these functions are doing. So I'm actually going to think about, well, what does the graph of cosine of x look like? So hopefully we remember from trigonometry, but if not, we'll just give a quick crash course here. Cosine of x, I know passes through 0, 1, and then I know that it's an oscillating function, meaning it repeats that the same behavior over and over and over again, and so it oscillates up and down between +1 and -1, right? +1 and -1. So it looks something like this. Now, I don't really need to be too detailed in like what are the x values of the intercepts and the max and the min values, because at the end of the day, what I'm really interested in is what's the end behavior of this function. So if I want to look at the end behavior, I might need to start by thinking about the domain. Domain of cosine of x is just negative infinity to positive infinity. There is no restriction on our domain. So that means that when I look at the limit, or the end behavior, excuse me, I'm going to look at the limit as x approaches positive infinity of cosine of x, and the limit as x approaches negative infinity of cosine of x. So let's take the right-hand end behavior here first. So if x approaches positive infinity, I can sort of say, okay, well, what y value are we approaching as x approaches positive infinity? And hopefully you're going to kind of have your eyebrow raised, because that seems like a silly question to ask. Well, gee, Mr. Huber, you just told me that that was an oscillating function, which means it keeps going up and down, up and down, up and down forever and ever, right? It's just going to keep oscillating between -1 and +1. So when I ask you, what y value are we approaching, it's really a trick question, because I'm not actually approaching a y value. It just keeps hopping down between -1 and +1. So in this case, if we're not approaching a single y value, we just keep hopping up and down between -1 and +1 like we are here, then that means that this limit does not exist, right? If I'm not approaching a single y value, we just say that the limit does not exist here. Same thing is going to happen then on the left side, right? Here I have a little bit less to look at, but I know the behavior is going to be the same. It's just going to oscillate up and down forever and ever. So since we don't approach a single y value here, again, this limit does not exist or is undefined, because we do not approach a single y value.